We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth currently racing through our solar system. Right now, there's a comet blazing across our sky that's got astronomers completely stumped. C20-25 or 2 Swan just survived a scorching close encounter with the sun and is heading straight toward us. Will we survive this encounter? Could this be our last chance to see something truly extraordinary? The discovery that almost didn't happen. On September 11, 2025, a Ukrainian astronomer named Vladimir Bezugly was looking through old images from a space telescope called SOHO, specifically from an instrument called SWAN. SWAN doesn't take the pretty pictures of space that we usually see. Instead, it watches hydrogen gas floating around the solar system, which sounds about as exciting as watching paint dry. But sometimes when a comet gets close to the sun, it starts spewing out hydrogen like a cosmic garden sprinkler, and SWAN can spot it. SWAN operates by detecting Lyman alpha radiation, a specific type of ultraviolet light that hydrogen atoms emit when they get excited by solar energy. This detection method works because comets carry enormous amounts of water ice. And when that ice gets heated by the sun, it breaks down into hydrogen and oxygen. The hydrogen atoms then get caught up in the solar wind and spread out in a huge invisible cloud that can extend for millions of miles around the comet itself. From SWAN's perspective aboard the SOHO spacecraft, this hydrogen envelope appears as a gradual brightening against the background glow of interplanetary space. Bezugly noticed something strange in the SWAN images. There was a fuzzy blob that hadn't been there before, and it was moving. Within hours, the discovery was confirmed and the comet got its official name, C25 or 2 Swan. But here's the wild part. When astronomers went back and looked at older images from another space telescope called Stereo A, they found SWAN had actually been visible since August. Nobody had noticed it because it was so faint and hidden in the sun's glare. The great orbital mystery. Here's where things get really weird. When astronomers find a new comet, the first thing they want to know is where it came from and when it will come back. With most comets, this is pretty straightforward math. You track the comet for a few weeks, measure its position very carefully and calculate its orbit. But SWAN is being a real troublemaker. The mathematical complexity behind orbital determination involves solving what astronomers call the two-body problem, where you're trying to figure out how an object moves under the gravitational influence of the sun. For most asteroids and short-period comets, this calculation is relatively straightforward because their orbits are well-defined ellipses that don't change much over time. But long-period comets like SWAN follow extremely stretched-out elliptical paths that are almost indistinguishable from parabolic or even hyperbolic trajectories when you're only observing a small portion of their orbit. Right now, two different groups of very smart astronomers are looking at the exact same comet and coming up with completely different answers about its orbit. The Jet Propulsion Laboratory, which handles a lot of space math for NASA, says this comet takes about 22,000 years to go around the sun once. That would make it an incredibly rare visitor that last showed up when humans were still figuring out how to make pottery. But the Minor Planet Center, which keeps track of all the asteroids and comets we know about, says SWAN only takes about 1,400 years to complete one trip around the sun. That's still a long time, but it means this comet might have visited us during the time of the Roman Empire or the early Middle Ages. The root of this disagreement lies in the extreme sensitivity of orbital calculations for nearly parabolic trajectory. When a comet's orbital eccentricity approaches 1, meaning its orbit is almost perfectly elongated, tiny errors in positional measurements can cascade into enormous differences in the calculated semi-major axis and orbital period. It's similar to trying to determine the exact shape of a nearly straight line when you can only see a tiny curved segment of it. So why can't these experts agree? It all comes down to which observations they trust more. The JPL team is using those older, fuzzier images from Stereo A that show the comet from farther away. The Minor Planet Center is only using the super precise measurements taken from Earth after SWAN was officially discovered. Both approaches make sense, but they give totally different results. It's like trying to figure out how fast a car is going by watching it from a mile away versus timing it with a stopwatch up close. What we're seeing right now, while the scientists argue about math, regular people with telescopes and binoculars are already enjoying the show right now. If you know where to look, you can see SWAN with a decent pair of binoculars. It looks like a fuzzy star with a greenish glow around it. And if you take a long exposure photograph, you can see a tail stretching out behind it that's about 2.5 degrees long. To put that in perspective, that tail appears about 5 times wider than the full moon. The physical processes creating this spectacular display are happening on an enormous scale. The comet's nucleus, which might only be a few miles across, is heating up as it approaches the sun and releasing thousands of tons of material every day. This material forms the coma, a temporary atmosphere around the comet that can grow to be larger than some planets. The tail forms when solar radiation pressure and the solar wind push this material away from the comet, creating streamers that can extend for millions of miles into space. The greenish color isn't just pretty. It tells us what SWAN is made of. When comets get close to the sun, the ice inside them starts to evaporate, creating a cloud of gas and dust around the solid nucleus. Different chemicals glow different colors when they get hit by sunlight, just like a neon sign. The green color comes from carbon molecules that have been broken apart by the sun's energy. People are reporting that SWAN is currently about magnitude 6, which means it's right at the limit of what you can see with your naked eye from a really dark location. Most folks will need binoculars or a small telescope to get a good look. But here's the exciting part. It's getting brighter as it gets closer to Earth. The spectroscopic analysis of comets involves breaking down the light they emit into its component wavelengths. Much like a prism splits white light into a rainbow, each chemical element and compound absorbs and emits light at very specific wavelengths, creating a unique fingerprint that allows astronomers to identify what materials are present in the comet's coma. Water vapor shows up as absorption lines in the infrared, while carbon compounds create the visible green emission that gives many comets their characteristic color. SWAN passed its closest point to the Sun on September 12, which means it's already survived the most dangerous part of its journey. Now it's heading our way, and it should reach its closest approach to Earth around October 20th. At that point it will be about 24 million miles away, which sounds like a lot, but is actually pretty close in space terms. The survival question. Not all comets make it through their journey around the Sun in one piece. When a comet gets too close to our star, several things can go wrong. The Sun's gravity can literally tear it apart if the comet isn't held together strongly enough. The rapid heating and cooling can cause the nucleus to crack like a rock thrown into a fire. Sometimes comets start spinning so fast from all the gas shooting out of them that they fly apart like a broken pinwheel. The physics of comet destruction involves several competing forces acting on what is essentially a dirty snowball traveling at tremendous speed. Tidal forces from the Sun's gravity try to stretch the comet apart while the internal gravity of the nucleus tries to hold it together. Meanwhile, the sublimation of ice creates gas jets that can spin the comet faster and faster, potentially exceeding the rotational breakup limit where centrifugal force overcomes gravitational binding. Add to this the thermal stress from extreme temperature changes. And it's actually surprising that any comets survive close approaches to the Sun at all. SWAN got closer to the Sun than the planet Mercury does. At its closest approach, the temperature on the comet's surface would have been hot enough to melt lead. For a comet that might be making this trip for the first time in thousands of years, that's a serious test of whether it can hold together. The good news is that SWAN seems to have passed this test. Astronomers haven't seen any signs that it's breaking up, like sudden brightness changes or multiple bright spots in the coma that would indicate fragments. Other comets haven't been so lucky. Comet 3I Atlas broke apart in 2020, creating a spectacular but short-lived show. Comet 2I Borisov, which came from another star system entirely, held together better, but still showed signs of stress during its visit in 2019. The size of the comet's nucleus plays a huge role in whether it survived. Bigger comets are generally more robust, while smaller ones are more likely to crumble. Unfortunately, we don't know how big SWAN's nucleus actually is. From this distance, even our best telescopes just see the bright cloud of gas and dust around it. The actual solid part could be anywhere from a few hundred meters across to several kilometers wide. Historical data from previous comet encounters suggest that objects with perihelion distances around half an astronomical unit have roughly a 25% chance of complete disintegration, with the probability increasing dramatically for smaller nuclei. The fact that SWAN has shown no immediate signs of fragmentation is encouraging, but comets can still break apart weeks or months after their closest solar approach as thermal stress cracks continue to propagate through the nuclear structure. Finding and observing the comet. If you want to see SWAN for yourself, now is the time to start looking. The comet is currently in the constellation Virgo, very close to the bright star Spica. In mid to late September, you'll want to look toward the west after sunset. The comet will be fairly low in the sky, so you'll need a clear view toward the horizon without trees or buildings in the way. The best time to look is about an hour after sunset, when the sky has darkened enough to see faint objects, but SWAN is still above the horizon. As we move into October, the comet will be visible higher in the sky and for longer periods each night. By the time it reaches its closest approach to Earth in late October, it should be visible most of the night. For casual observers, a pair of 7 by 50 or 10 by 50 binoculars will show the comet's fuzzy coma quite well. If you have a small telescope, Use the lowest magnification you have to get the best view of the tail. The tail is the most impressive part, but it's also the most challenging to see because it's spread out over such a large area of sky. The optimal viewing conditions depend heavily on your local light pollution levels and atmospheric conditions. From urban areas, Swan may be difficult to spot without optical aid due to sky glow washing out the fainter parts of the coma and tail. Rural observers under dark skies will have a significant advantage, potentially seeing details invisible to city dwellers. The comet's altitude above the horizon also affects visibility with atmospheric extinction reducing brightness when the comet is low in the sky during evening twilight hours. Photographers are already getting spectacular images of Swan. If you want to try photographing it yourself, you'll need a camera that can take long exposures and a way to track the comet's movement across the sky. Even a basic camera lens in the 200 to 300 mm range can capture the tail if you stack multiple exposures together. The comet is also passing near some other interesting objects in the sky. In late September it will appear close to the planet Mars, which will make for some beautiful photographs with both objects in the same frame. These kinds of cosmic alignments don't happen very often, so it's worth taking advantage of the opportunity. Every precise position measurement of Swan helps refine its orbit and resolve the current disagreement about its period. As more observatories around the world contribute measurements, the uncertainty in the orbital calculation shrinks rapidly. Within a few more weeks, astronomers should have a definitive answer about whether this comet takes 1,400 years or 20,000 years to orbit the Sun. This is citizen science at its best. Amateur astronomers around the world with modest telescopes can contribute measurements that help solve the puzzle. The October meteor mystery. Here's something that has meteor watchers excited and skeptical at the same time. Around October 4th through 6th, Earth will pass through the same plane as Swan's orbit. This creates the possibility, and that's a big emphasis on possibility, that we might see some meteors caused by tiny pieces of dust that the comet left behind on previous visits. The problem is that for a long-period comet like this one, any dust trail would be incredibly old and spread out. Most meteor showers come from comets that visit us regularly, leaving fresh trails of debris every time they come around. The famous Perseid meteor shower in August comes from comet Swift-Tuttle, which returns every 133 years and has been leaving dust in its wake for thousands of years. Meteoroid stream dynamics are governed by complex gravitational and non-gravitational forces that act over astronomical time scale. When a comet releases particles during perihelion passage, those particles initially follow orbits very similar to the parent comet. However, solar radiation pressure affects different-sized particles differently, causing the stream to gradually spread out, both along the comet's orbital path and perpendicular to it. Larger particles are less affected by radiation pressure and maintain orbits closer to the original trajectory, while smaller particles get pushed into slightly different orbits that may never intersect Earth's path. Swan might not have been in the inner solar system for over 1,000 years, depending on which orbital calculation turns out to be correct. That means any dust it left behind would have had centuries to spread out and dissipate. It's like trying to walk through the wake of a boat that passed by yesterday. There might be some ripples left, but they'll be pretty faint. The isotopic ratios found in Cumtri materials provide additional clues about formation conditions. Heavy water, which contains deuterium instead of regular hydrogen, forms preferentially at very low temperatures. By measuring the ratio of heavy water to regular water in Swan's emissions, scientists can determine the temperature of the region where the comet originally formed. Similar measurements of carbon and nitrogen isotopes help constrain the chemical processes that occurred in the early solar nebula. Swan will gradually fade after its closest approach to Earth in late October, but it should remain visible in telescopes for several more months as it heads back out to the distant parts of the solar system. Whether it takes 1,400 years or 20,000 years to return, most of us won't be around to see it again. This is likely our one chance to observe this particular visitor from the deep freeze of the outer solar system. What are your thoughts on Swan? Let us know in the comments down below.